Welcome to this video on the quantum mechanics of transient absorption spectroscopy, or TA. We will explore the quantum phenomena that govern this powerful technique. Transient absorption interrogates the evolving state of a photoexcited molecule. A pump pulse prepares a non-equilibrium state, and a delayed probe pulse measures available optical transitions from that evolving state. A common misconception is that TA only measures populations. In reality, TA measures the optical response of a non-equilibrium density matrix. The detected signal is proportional to the third-order polarization P3. The transient optical response is governed by this mathematical engine, which includes the nuclear kinetic energy, the electronic Hamiltonian, environment terms, and the coupling of the system to the pump and probe fields. Nuclear wave packets navigate coupled excited state surfaces. TA observes how these wave packets change the allowed probe transitions over time. Born-Oppenheimer breakdown occurs when states couple strongly, leading to non-adiabatic transfer. Spectra reflect dipole-allowed transitions at the current geometry. The measured optical response depends on the photoexcited joint density of states and the transition dipole matrix elements. The final response is dictated by overlapping pathway contributions. Ground state bleach, stimulated emission, and excited state absorption are the three textbook TA contributions. These are overlapping contributions to the identical third-order response R3. Ground state bleach reflects a depleted initial population. The pump heavily depletes the ground state population, leading to fewer molecules available to absorb. This yields a negative delta A signal. Stimulated emission amplifies the transmitted probe light. The probe stimulates emission from an excited state back down to a lower state, increasing the total transmitted light and yielding a negative delta A signal. Excited state absorption promotes population to higher states. The probe light promotes population from an existing excited state up to a higher lying state, resulting in a positive delta A signal. We track Liouville space pathways through density matrices using 4 steps. The pump creates optical coherence, which collapses to population. This evolves, and the probe converts it into a new optical coherence that modulates transmission. Near time zero, additional coherent artifacts inevitably appear due to pump-probe field overlap, cross-phase modulation, and non-resonant effects. Exercise extreme caution when interpreting early-time coherent oscillations. The probe interrogates a dynamic vibronic system, not a frozen electronic state. The excited state wave packet moves continuously on a multi-dimensional potential energy surface, with simultaneous physical changes occurring. A shifting transient absorption band occurs as the multi-dimensional geometry changes. Transition energies and transition dipoles both change simultaneously, leading to shifts due to changes in state energy, dipole, or vibronic overlap. State mixing makes organic emitters exceptionally sensitive. Local excitation and charge transfer characters mix strongly and respond differently to changes in geometry and environment. TA maps these complex interactions through the evolving optical response. Welcome to Decoding the Shadow, Transient Absorption Spectroscopy in Organic Emitters. This video will explore how transient absorption spectroscopy helps us understand excited states in organic materials. Transient absorption, TA spectroscopy, moves beyond focusing on a single peak, revealing the exact nature and ordering of excited states. It shows whether a state is LE-like or CT-like, and where dark triplets reside. We use the DMA-CTRZ benchmark to reveal the hidden map. This technique identifies excited states driving reverse intersystem crossing, shows strong environment dependence, and resolves conformer interconversion on the picosecond scale. Photoluminescence, or PL, only sees the visible light from bright singlets, leaving a blind spot. Transient absorption, or TA, accesses the dark actors, like triplet states, that emission completely misses. To achieve efficient reverse intersystem crossing, a small energy gap is not enough. Direct conversion is forbidden, so the mechanism requires a nearby LE state that mixes with CT to mediate upconversion to CT. TA exposes hidden loss pathways. Emission profiles miss bottlenecks, where long-lived triplet channels are poor at converting back to bright singlets. Apparent promise under optical excitation often overestimates true OLED operation. There is a device disconnect. Optical excitation starts with 100% singlets in dilute solutions. However, OLED charge recombination statistically forces us to manage a 75% triplet population. Our interpretation playbook includes 3 components: Ground state bleach, or GSB, is negative bands near steady-state absorption. Stimulated emission, or SE, are red-shifted negative bands. Excited state absorption, or ESA, is positive bands from whatever manifold is populated at that delay. Beware the danger of vicious overlap, where ground state bleach can hide stimulated emission. Excited state absorption is often a cleaner reporter of relaxation because it is spectrally separated. We must decompose the full spectrum globally. When dealing with a thin organic film, the measured change in transmission is not identical to the intrinsic change in absorption. Distortions arise from interference effects and pump-induced refractive index changes. The analytical solution for films involves using the Kramers-Kronig mathematical filter. This converts distorted raw data into clean, quantitative oscillator strengths and is the only defensible route for quantitative results. TA spectroscopy measures the probe-accessible transition structure of a time-evolving non-equilibrium vibronic density matrix. True understanding requires first principles modeling of the full chain, including environment effects and non-adiabatic couplings. The real prize is that TA tells us the state, its character, how geometry affects it, the role of dark triplets, and if the optical pathway is relevant to the device. The spectrum is not the story, it is the shadow cast by the story. Welcome to this video on Transient Absorption Spectroscopy, exploring the journey from quantum mechanics to ab initio simulation. We will bridge third-order nonlinear optical theory with modern computational workflows. The time-resolved timeline involves 3 steps. First, a pump pulse prepares a non-equilibrium state. Second, dark evolution occurs as the system evolves dynamically on the excited state. Finally, a delayed probe pulse interrogates the optical transitions available from that evolving state. Transient absorption is not merely measuring populations. What is actually measured is the optical response of a non-equilibrium density matrix. The signal is proportional to the third-order polarization and third-order response function. There are 3 textbook contributions: ground state bleach, stimulated emission, and excited state absorption. These are overlapping pathway contributions to the same third-order response, not separate experimental knobs. The Hamiltonian, h of t, includes terms for nuclear kinetic energy, electronic Hamiltonian at nuclear geometry r, environment effects, and coupling to the pump and probe fields. The spectrum reflects which dipole-allowed transitions are available at the current geometry and environment. The probe interrogates a vibronic system, where wave packet motion dynamically changes bond lengths and coordinates. This results in transition energies and dipoles dynamically changing as the geometry evolves. The Born-Oppenheimer picture breaks down at points like conical intersections. Non-adiabatic transfer and intersystem crossing occur here. Practical calculations use mixed quantum classical non-adiabatic dynamics to address these phenomena. The semi-classical signal equation shows the balance between positive contributions from excited state absorption and negative contributions from stimulated emission and ground state bleach. This relies on geometry-dependent transition properties sampled along non-adiabatic trajectories. 2 modeling philosophies exist: the doorway window picture, which is trajectory-based and connects to nonlinear spectroscopy theory, and explicit real-time field propagation, which is computationally expensive but ideal for short-time dynamics and explicit light interaction. For organic emitters, the electronic structure choice is critical for state ordering. Moderate-cost methods like TDDFT, ADC2, and CC2 are used. Case studies show that different methods can produce materially different population dynamics and transient absorption signals. The practical A-flat initio workflow involves 4 steps. First, generating a structural ensemble. Second, linear verification of the electronic structure method. Third, on-the-fly propagation of photo-excited dynamics. Finally, spectral post-processing to evaluate probe transitions and convolve with line-shape functions. The grand synthesis connects microscopic physical ingredients like PES gradients and transition dipole moments with computational implementation. The computational flowchart is essentially the execution of the quantum Hamiltonian, allowing for a direct readout of the non-equilibrium density matrix evolving in real time.